Hi all. So welcome to this video related to the subject information theory and coding. And the topic discussed here is source coding and the source coding theorem, Shanon's source coding theorem. Okay, so let's begin with a discussion on source coding and what is this function of a source encoder. Okay, so we know source encoder is that part of the transmitter that performs the function of generating a binary representation, an efficient binary representation for your data from the information source. And this process of assigning that efficient data representation to your information source is what you call it as source coding. Okay, so let's speak with a simple example. Like whatever be your information from the information source, we are just giving it a binary representation, and that is source coding. So let me take a simple text like let it be command. This is my data from the information source, and I am giving a binary representation 0, 1 to this 7-letter word. And this transformation or this reformation of your data into this binary representation is what you call it as source coding. And the entity of your transmitter that performs this function, what you call it as the source coder or the source encoder. Okay, so let's begin with, or let's move on to the technical aspects of regarding an information source. We know that information source can be represented as an entity that produces, if this is your information source, we can represent your information source as an entity that is producing some K symbols with an output SK, right? And this is being given to a source encoder, that takes these symbols from the information source as the input and produces some binary representation BK. Okay, that is the output of the information source will be a set of symbols S0, S1, etc. It can be up to some K symbols, so it is K minus 1, and these symbols are being converted to the binary representation. Okay, so let me take a simple example like I'm taking an information source whose alphabet contains 4 symbols like S0, S1, S2 and S3. Okay, just I'm taking 4 symbols. Okay, and now we can just make it as a tabular representation, like you have your symbols S0, S1, S2 and S3, and the output of the encoder, it is like for S0 the binary representation has 0, for S1 it is 1, for S2 it is something like 0, 1, and for S3 it is something like 1, 1. So this is the binary representation. Okay, so this is your output from the information source, and this is the output of your encoder. Okay, so each of these binary representation corresponding to a symbol, you call it as a code word. Okay, so each of these binary representation corresponding to a symbol, you call it as a code word. And this complete set of the encoder output containing different code words for different symbols is what you call it as a code. So code is actually a collection of different code words. Okay, and here you can see the length of this code word is 1. So I represent it as L as the length of the code word. So L actually indicates what? The number of bits with which you are representing a particular symbol. Okay, so here for S0 the length of the code word is 0, but for S2 you can see the length of the code word is 2, and similarly for S3 it is 2. Okay, so these are the code words and this set forms the code. Okay, now this codes, it can be in 2 different ways, like it can be fixed length codes. It can be like fixed length codes as mentioned here, or it can be like variable length codes. Okay, fixed length, okay, just let me tell you, this example what I have taken here is a variable length coding. You can see because each of the symbol is having a different length for their code words. Okay, but what will be a fixed length code? like if I'm taking an example, like my S0, S1, S2, S3 is having 0, 0, 0, 1, 1, 0, 1, 1. This code is a fixed length code because you can see every symbol is having the same, every code word is having the same length, and that is what you call it as a fixed length code. But what example we have considered here is a variable length code. So in the case of variable length code, there should be some criteria, like if you see S0 is having only 1 bit representation, but S2 is having a 2 bit representation. So obviously there should be some criteria that is deciding how much bits you should assign to each of these symbols. Okay, so this is actually based on your probability theories. Okay, so normally what we do is a symbol with high probability will be given a short code word, and a symbol with low probability will be given a longer code word. That is how variable length coding is normally done. Okay, a symbol with high probability will be given a short code word for representation, and a symbol with lower probability will be given a longer code word. Okay, so that is how you do the variable length coding. Now again, one more thing, what we speak about the source encoder is the two properties that your source encoder should bear. Okay, one, it is definitely that the output of the encoder should be in the binary form. Okay, we have already said that is a function of the binary encoder that it produces binary output. So first property is that the output of the encoder should be in the binary format, and second property is that the output that the encoder produces should be uniquely decodable. So let's investigate what is this property of uniquely decodable. Uniquely decodable. Okay, uniquely decodable in the sense, again let's take this example. Let's take. Okay, suppose I have transmitted a binary sequence like 0 1 0 1 0 1 1 1. Okay, 0 1 0 1 0 1 1 1. So this is the sequence what I have transmitted. Okay, so we know that if we have done a process like encoding at the transmitter, we should do the reverse process of decoding at the receiver. So obviously the receiver is going to perform decoding. Now when the receiver look into this binary sequence, from this code what has been created, we know S0 can be decoded as the symbol S0. A 1 can be decoded as a symbol S1. Okay, so actually this sequence has two ways in which we can decode it. Okay, one way I am decoding it as S0, it is S1, again S0, again S1, S0, S1, S1, S1. You understand that for each of these binary representation, we are just decoding which symbol it is. Just the reverse process. Okay, so this is actually one way of decoding. Let me do another way of decoding. Like 0 1, we have already a symbol. 0 1 is your S2. This is S2. Again 0 1 is S2. Again 0 1 is S2. 1 1, I think it is S3. See what happens? Like we have a confusion regarding how we should decode this particular sequence. This is because of this particular code what the encoder has produced. So actually at the decoder, this kind of a confusion should not exist. That is, the codes should be uniquely decodable. In that way the code should be generated. Okay, so that is one property of the encoder that is required. That is, we should generate the symbols in a way that they are uniquely decodable at the receiver. Okay. Now let's move on to the source encoding theorem. Source coding theorem. Okay, before moving on to this theorem, let's see what is the motivation towards the source coding theorem. Okay, so again let's consider an information source producing some succession of symbols like S1, S2, S3, etc. It's producing something like K symbols. Okay, and each of these symbols are having probability like P0, P1, P2, etc. pk minus 1. This is capital K, sorry. Okay. Now, just as in this similar case, this similar example, I'm going to present a table like it is S0, S1, S2, S3, and I have the symbols 0, 1, 0, 1, 1, 1. Okay. Now, what is the length of each of the symbols? For S0, it is 1. For S1, again 1, it is 2, 2. Okay. And they have the probabilities like 0.3, 0.3, 0.2, 0.2. Okay. Now we have called a concept called the average code word length, which is given by summation over k is equal to 0 to k minus 1 pk into lk. This is what we call it as the average code word length. And this particular term or factor is what we use to calculate the efficiency of the code. Okay. So from here we can see how will you calculate the average code word length. It is 0.3 into 1 pk into lk. This is p probability. Okay. So 0.3 into 1 plus 0.3 into 1 plus 0.2 into 2 plus 0.2 into 2. Right. That's how you calculate this L bar. So this L bar is a very important factor which actually determines the efficiency of the code word of this particular code. Okay. So normally the efficiency is given by eta is equal to L minimum divided by L bar. Okay, so that's the efficiency of the code. And from this equation, it's very clear that if you want your efficiency to be reaching 100% or reaching 1, we need to make L bar what? Minimum, or you have to reduce L bar. Okay, so such a code which has a minimum L bar, that is just, we were speaking about the function of the source coding. I told you that our aim is to give a very compact and a very minute representation for the data. Okay, so it's not fair like for a 7-letter word to give a 7-bit representation. Okay, our aim is to give for a 7-bit word, we should give something like a 2-bit representation or even a 1-bit binary representation. Okay, so that's our aim. So as the length of the code word increases, the efficiency of our code is decreasing. Okay, so this efficiency, in order for the efficiency to be less than 100% or equal to 100%, your L bar should be kept as minimum as possible. But there is one condition, that your L bar, this is the condition, that is your L bar should be greater than or equal to L minimum. Okay, your L bar should be kept as low as possible, but at the same time it should be greater than or equal to L minimum. That is the condition for a good code or an optimal code. Now, what should be this L minimum? Like we are randomly talking about L minimum. Now, what should be this L minimum? Okay, so this value of L minimum is given by the Shanons source coding theorem. Okay, so according to Shanon's source coding theorem, your L bar, it is bounded as L bar is greater than or equal to h of s. Okay, so this is your Shannon's first theorem or Shannon's source coding theorem. Okay, that is your average code word length should be bounded as it should be greater than or equal to h of s, where we know h of s is the entropy of the source. Okay, under this condition you can say that you have generated an optimal set of code, or sorry, an optimal set of code words. Okay, then the equation of your efficiency can be written as, it becomes like h of s divided by L bar. Okay, so that is the statement for your for your source coding theorem. And one more thing, like if I'm saying that L bar should be greater than or equal to h of s, I should say that then L bar should be always less than what? H of s plus 1. Right? So combining these two bounds, I can write your L bar, it should be greater than or equal to h of s, but it should be less than your h of s plus 1. Okay, so this is the complete statement for your source coding theorem. Okay, now let's take to the proof for the source coding theorem. Now let's see the proof of the source coding theorem. So what we have to prove, that it is L bar less than or equal to h of s should be your h of s should be less than or equal to L bar should be less than h of s plus 1. So this is what you have to prove, where this portion represents a lower bound and this represents an upper bound. Okay, so first let's prove the lower bound. Okay, that is what we have to prove is, let's take the lower bound, that is L bar is greater than or equal to h of s. Okay, or in other way we can write L bar minus h of s should be greater than or equal to 0. Either way. Okay, so let's start with the proof. Okay, now let me take L bar minus h of s. This can be written as, we know the equation for L bar, it is summation k is equal to 0 to k minus 1 pk into lk minus equation for h of s is entropy k equal to 0 to k minus 1. It is pk log to the base 2 1 by pk. Right. Now we know that here let's consider a factor like, we have a factor like 1. See, this is something like we are multiplying this factor with 1. And one more thing what we know is log 2 to the base 2 is equal to 1. Okay, so I'm just rewriting this term as, it is summation k is equal to 0 to k minus 1 pk lk log to the base 2 and just a modification for your logarithm term k equal to 0 to k minus 1 pk log to the base 2 pk. I can write it in this way, right? Now what is actually n log x? It is log x raised to n, right? So again I am modifying this term as summation k is equal to 0 to k minus 1 pk log 2 to the base 2 raised to lk, because this term I have taken together, plus this term becomes k is equal to 0 to k minus 1 pk log to the base 2 pk. Okay, now let's group the common terms. So it becomes k is equal to 0 to k minus 1 pk into log 2 to the base 2 raised to lk plus log pk to the base 2. Okay, now what is log a plus log b? It is log ab. So this becomes, this is equal to, so we are doing with L bar minus h of s, just remember. So it becomes k is equal to 0 to k minus 1. It is pk log to the base 2 pk into 2 raised to lk. Okay, now I am just trying to change the base of the logarithm to natural log, so that what happens is this becomes 1 by log 2 summation k is equal to 0 to k minus 1. It is pk log to the base, it's natural log, pk into 2 raised to lk. This is a simple log mathematics, that is if you have log a to the base b can be written as log a by log b. So we are changing where this base should be natural log. So that's what we have done here. Okay, so we got your L bar minus h of s in this way. Now what you have to go is, you are going to do is, we have an inequality from the natural logarithm as your log x will be always less than or equal to x minus 1, which is actually a proven inequality. If we take the graph of log x and x minus 1, we can always say that log x will be less than x minus 1. Okay, so we can just modify this logarithm as, I can write it as log 1 by x less than or equal to x minus 1. Alright. Now again, this is like log 1 by x. I'm just taking this negative to the side. So the inequality changes and it becomes 1 minus x. Okay. Now what, in the next step, what you're going to do is, I'm going to substitute x is equal to 1 by pk into 2 raised to lk. Okay. So in this inequality, I'm going to substitute for x as 1 by pk 2 raised to lk. So what happens? It becomes log pk 2 raised to lk is greater than or equal to 1 minus 1 by pk 2 raised to lk. Alright. Now on this, both the sides of this inequality, I am going to multiply with a factor 1 by log 2 summation over k equal to 0 to k minus 1 pk. Okay, on both the sides of inequality, I am going to multiply with this factor. So it becomes 1 by log 2 summation over k is equal to 0 to k minus 1 pk into log pk 2 raised to lk greater than or equal to, again 1 by log 2 summation k is equal to 0 to k minus 1 pk. It is 1 minus 1 by pk 2 raised to lk. Okay. Now what is actually this part? This is something what we got here, that is L bar minus h of s. Right. So I can write it as L bar minus h of s. Okay. This part I can write it as L bar minus h of s. Okay. Which is greater than or equal to. Now what about this? I am going to open the bracket and substitute. Okay. So it becomes 1 by log 2 summation k is equal to 0 to k minus 1 pk minus 1 by log 2 summation k is equal to 0 to k minus 1 pk into 1 by pk 2 raised to lk. Okay. Now this is, again, we know what is summation over k, pk is always 1 minus, now this term can be reduced to log 2 summation k is equal to 0 to k minus 1. It becomes like, if you cancel your pk, it becomes 2 raised to minus lk. Now we have something called Crafts-Macmillan inequality, which shows that your summation over k 2 raised to minus lk is always less than or equal to 1. Okay, so you can take it as 1. So when you substitute for 1, this, it becomes 1 minus 1, which shows that your L bar minus h of s is greater than or equal to 0. So you proved the second half, you proved the lower bound. Now we have to prove the upper bound. Okay, now the upper bound, now the upper bound is like, your upper bound is L bar less than h of s plus 1. So this is your upper bound. Okay. So again, let's consider the Crafts inequality. So according to Crafts inequality, your summation over k 2 raised to minus lk is always less than or equal to 1. And we already know that summation over k pk is equal to 1. So for this one, I am giving the summation over here. So I can say summation over k 2 raised to minus lk is less than or equal to summation over k pk. Okay, so from this inequality, it's very clear that your 2 raised to minus lk is less than or equal to pk. Right. So if I am saying that your pk should be greater than or equal to 2 raised to minus lk, I should say that your pk should be less than 2 raised to minus LK plus 1. Okay, so we are inferring from this inequality, we can infer that if your pk is greater than or equal to 2 raised to minus lk, your pk should be obviously less than 2 raised to minus lk plus 1. Okay, so now let's take this inequality and I am going to multiply a log to the base 2 on both the sides of this inequality. So it becomes log 2 pk less than, log pk to the base 2 less than log 2 raised to minus lk plus 1 to the base 2. Okay, now again a slight modification. This is log pk to the base 2 less than, I can write it as minus lk plus 1 into log 2 to the base 2. Okay, so again this becomes log pk to the base 2 less than minus lk plus 1. Okay, now again let's continue. I'm going to take this 1 to this side. Okay, so it becomes log 2 to the base log pk to the base 2 minus 1 less than minus lk. All right. Now I'm going to take this negative side to this side. So obviously your inequality will change the direction. So it becomes 1 minus log pk to the base 2 greater than lk. Okay. So for convenience, I am writing it as lk is less than 1 minus log pk to the base 2. Okay. Now on both the sides of this inequality, I am going to multiply with a term summation over k pk, but before that I am going to change this sign over here, like it becomes lk less than 1 plus log 1 by pk to the base 2. This is 1, it's 1 by pk to the base 2. Alright, now again multiplying on both sides, this becomes summation over k pk lk less than summation over k pk into 1 plus log 1 by pk to the base 2. Alright. Now what is summation over k pk lk? It is your L bar. So L bar less than summation over k pk plus summation over k pk into log to the base 2 1 by pk. Okay. So this is L bar less than, so this term it's obviously 1 plus, what is this? This is your h of s. Okay, so what you got it as your L bar is less than h of s plus 1. So thus we proved the upper bound for your source coding theorem. That is, your source coding theorem is bounded as L bar h of s less than or equal to L bar less than h of s plus 1. So we have proved both the bounds, that is your upper bound and the lower bound. Thank you.